Okay, so this is 1574 here, and we are given two disks here, A and B, and we're given their velocities prior to impact. And we know after impact, VB is traveling 30 degrees away from the y-axis here, so after impact. And A will just be along the x-axis after impact because the line of impact is the x-axis. We know the masses of the disks are equal. They're both 0.5 kilograms, and what we're looking for is the coefficient of restitution. So we're going to perform the conservation of momentum. The 1 represents prior to impact, and the 2 represents after impact here. And we're going to break this down in both the x direction and y direction. So let's first start out with the x direction. All right, so VA here, or we have disk A, and we know the mass is 0.5, the velocity is 6 in the x direction, all right, but it is in the negative x direction, so we need to make sure we put a negative sign out front here. Disk B here is 4 meters per second, so we have the mass of 0.5 times the velocity of 4, but in the x direction, it's just a component of that, which is 3/5. Then after impact, we have 0.5 for the mass of A, and we know the direction afterwards. We're going to assume that A just travels positive x after the collision. So we have VA at time 2 in the x direction. That's what that notation stands for. And then we know VB is the component of that is actually going to be in the negative x direction. So we have negative 0.5 VB 2 in the x direction. All right, so let's move on to the y direction now. I guess we can simplify that a little bit more. This comes out to be negative 3.60 equals VA 2x minus VB 2x. That's 3.6 there. All right, let's move to the y direction. So the disk A does not have any initial velocity in the y direction, and since the impact is right along the x-axis, afterwards it's not going to have any y direction velocity either. So we can neglect A for this, and we only need to do the conservation of momentum for B. So prior to impact, we have a velocity in the y direction here, which is 4/5 of 4 meters per second. So let's do that. Okay, so we have 0.5 times 4 times 4/5 there. Okay, and then afterwards, we still have a mass of 0.5, and then we have VB after impact in the y direction. Solving for this, we get VB 2y comes out to be 3.2 meters per second in the y direction. So that's the component in the y direction. So if we just draw that triangle quick, okay, so this is VB after impact. This is 30 degrees. And this over here is 3.2. And what this represents is VB 2x up here. So we know the tangent of 30 degrees equals opposite, which is VB 2x divided by adjacent, which is 3.2 right here. So solving for that, we have VB 2x comes out to be 1.8475 meters per second. And notice that's to the left here. That's going to the left. So we better put a negative on that to indicate that's negative in the negative x direction. So we'll put a negative on there. Okay, and then plugging this back up into this equation, we get VA 2x comes out to be negative 1.752 meters per second. So this negative represents that after the impact, A actually moves in the negative x direction after impact. Okay, so we have what we need here. So to figure out the coefficient of restitution, remember, it's VA after the impact minus VB after the impact over VB before the impact minus VA before the impact. And we have these x and y components, but remember the coefficient of restitution only applies along the line of impact. And for this problem, the line of impact is the x-axis here. So we're only using the x versions of these variables after the impact and before the impact. So VA2x is negative 1.752 minus VB2x, which is minus a negative 1.8475 divided by prior to the impact. VB1 is 4 times, the component of that is 3 over 5. Right? So that's the x direction component of this, 3 over 5 times 4, minus VA1, which is negative 6. Right? And solving for this, we get a coefficient of restitution of 0.0113. And that is our answer for 1574.